In classical mechanics, linear momentum or translational momentum is the product of the mass and velocity of an object. For example, a heavy truck moving rapidly has a large momentum. It takes a large or prolonged force to get the truck up to this speed, and it takes a large or prolonged force to bring it to a stop afterwards. If the truck were lighter, or moving more slowly, then it would have less momentum. Like velocity, linear momentum is a vector quantity, possessing a direction as well as a magnitude, where p is the three-dimensional vector stating the object's momentum in the three directions, a three-dimensional space. V is the three-dimensional velocity vector giving the object's rate of movement in each direction, and m is the object's mass. Linear momentum is also a conserved quantity, meaning that if a closed system is not affected by external forces, its total linear momentum cannot change. In classical mechanics, conservation of linear momentum is implied by Newton's laws. It also holds in special relativity and, with appropriate definitions, a linear momentum conservation law holds in electrodynamics, quantum mechanics, quantum field theory, and general relativity. It is ultimately an expression of one of the fundamental symmetries of space and time, that of translational symmetry. Newtonian mechanics. Momentum has a direction as well as magnitude. Quantities that have both a magnitude and a direction are known as vector quantities. Because momentum has a direction, it can be used to predict the resulting direction of objects after they collide, as well as their speeds. Below, the basic properties of momentum are described in one dimension. The vector equations are almost identical to the scalar equations. Single particle. The momentum of a particle is traditionally represented by the letter p. It is the product of two quantities, the mass and velocity. The units of momentum are the product of the units of mass and velocity. In SI units, if the mass is in kilograms and the velocity in meters per second, then the momentum is in kilogram-meters second. An equivalent derived unit is the Newton second. In CGS units, if the mass is in grams and the velocity in centimeters per second, then the momentum is in gram-centimeters second or dyne seconds. Being a vector, momentum has magnitude and direction. For example, a 1 kilogram model airplane, traveling due north at 1 meter per second in straight and level flight, has a momentum of 1 kilogram meter per second due north measured from the ground. Many particles. The momentum of a system of particles is the sum of their momenta. If two particles have masses m1 and m2, and velocities v1 and v2, the total momentum is the momenta of more than two particles can be added in the same way. A system of particles has a center of mass, a point determined by the weighted sum of their positions. If all the particles are moving, the center of mass will generally be moving as well. If the center of mass is moving at velocity v(cm), the momentum is. This is known as Euler's first law. Relation to force. If a force F is applied to a particle for a time interval delta t, the momentum of the particle changes by an amount in differential form. This is Newton's second law. The rate of change of the momentum of a particle is proportional to the force F acting on it. If the force depends on time, the change in momentum between times t1 and t2 is under the assumption of constant mass m. It is equivalent to right, so the force is equal to mass times acceleration. Example: a model airplane of 1 kilogram accelerates from rest to a velocity of 6 meters per second due north into s. The net force required to produce this acceleration is 3 newtons due north. The change in momentum is 6 kilograms meter per second. The rate of change of momentum is 3 per second equals 3n. Conservation. In a closed system, the total momentum is constant. This fact, known as the law of conservation of momentum, is implied by Newton's laws of motion. Suppose, for example, that two particles interact. Because of the third law, the forces between them are equal and opposite. If the particles are numbered 1 and 2, the second law states that F1 equals dp1 dt and F2 equals dp2 dt. Therefore, with the negative sign indicating that the forces oppose. Equivalently, if the velocities of the particles are u1 and u2 before the interaction, and afterwards they are v1 and v2, then this law holds, no matter how complicated the forces between particles. Similarly, if there are several particles, the momentum exchanged between each pair of particles adds up to zero, so the total change in momentum is zero. This conservation law applies to all interactions, including collisions and separations caused by explosive forces. It can also be generalized to situations where Newton's laws do not hold, for example in the theory of relativity and in electrodynamics. Dependence on reference frame momentum is a measurable quantity, and the measurement depends on the motion of the observer. For example, if an apple is sitting in a glass elevator that is descending, an outside observer, looking into the elevator, sees the apple moving, so, to that observer, the apple has a non-zero momentum. To someone inside the elevator, the apple does not move, so, it has zero momentum. The two observers each have a frame of reference, in which they observe motions, and, if the elevator is descending steadily, they will see behavior that is consistent with those same physical laws. Suppose a particle has position x in a stationary frame of reference. From the point of view of another frame of reference, moving at a uniform speed u, the position changes with time, as this is called a Galilean transformation. If the particle is moving at speed dx, dt equals v in the first frame of reference, in the second, it is moving at speed since u does not change. The accelerations are the same. Thus, momentum is conserved in both reference frames. Moreover, as long as the force has the same form in both frames, Newton's second law is unchanged. Forces such as Newtonian gravity, which depend only on the scalar distance between objects, satisfy this criterion. This independence of reference frame is called Newtonian relativity or Galilean invariance. A change of reference frame can, often, simplify calculations of motion. For example, in a collision of two particles, a reference frame can be chosen, where one particle begins at rest. Another, commonly used reference frame, is the center of mass frame, one that is moving with the center of mass. In this frame, the total momentum is zero. Application to collisions by itself. The law of conservation of momentum is not enough to determine the motion of particles after a collision. Another property of the motion, kinetic energy, must be known. This is not necessarily conserved. If it is conserved, the collision is called an elastic collision. If not, it is an inelastic collision. Elastic collisions. An elastic collision is one in which no kinetic energy is lost. Perfectly elastic collisions can occur when the objects do not touch each other, as for example in atomic or nuclear scattering where electric repulsion keeps them apart. A slingshot maneuver of a satellite around a planet can also be viewed as a perfectly elastic collision from a distance. A collision between two pool balls is a good example of an almost totally elastic collision, due to their high rigidity, but when bodies come in contact there is always some dissipation. A head-on elastic collision between two bodies can be represented by velocities in one dimension, along a line passing through the bodies. If the velocities are u1 and u2 before the collision and v1 and v2 after, the equations expressing conservation of momentum and kinetic energy are. A change of reference frame can often simplify the analysis of a collision. For example, suppose there are two bodies of equal mass m, one stationary and one approaching the other at a speed v. The center of mass is moving at speed v2 and both bodies are moving towards it at speed v2. Because of the symmetry, after the collision both must be moving away from the center of mass at the same speed. Adding the speed of the center of mass to both, we find that the body that was moving is now stopped and the other is moving away at speed v. The bodies have exchanged their velocities. Regardless of the velocities of the bodies, a switch to the center of mass frame leads us to the same conclusion. Therefore, the final velocities are given by in general, when the initial velocities are known. The final velocities are given by if one body has much greater mass than the other. Its velocity will be little affected by a collision while the other body will experience a large change. Inelastic collisions. In an inelastic collision, some of the kinetic energy of the colliding bodies is converted into other forms of energy such as heat or sound. Examples include traffic collisions, in which the effect of lost kinetic energy can be seen in the damage to the vehicles, electrons losing some of their energy to atoms, and particle accelerators in which the kinetic energy is converted into mass in the form of new particles. In a perfectly inelastic collision, both bodies have the same motion afterwards. If one body is motionless to begin with, the equation for conservation of momentum is so in a frame of reference moving at the speed v. The objects are brought to rest by the collision and 100% of the kinetic energy is converted. One measure of the inelasticity of the collision is the coefficient of restitution Cr, defined as the ratio of relative velocity of separation to relative velocity of approach. In applying this measure to ball sports, this can be easily measured using the following formula. The momentum and energy equations also apply to the motions of objects that begin together and then move apart. For example, an explosion is the result of a chain reaction that transforms potential energy stored in chemical, mechanical, or nuclear form into kinetic energy, acoustic energy, and electromagnetic radiation. Rockets also make use of conservation of momentum. Propellant is thrust outward, gaining momentum, and an equal and opposite momentum is imparted to the rocket. Multiple dimensions. Real motion has both direction and velocity and must be represented by a vector. In a coordinate system with x, y, z axes, velocity has components vx in the x direction, vy in the y direction, vz in the z direction. The vector is represented by a boldface symbol. Similarly, the momentum is a vector quantity and is represented by a boldface symbol. The equations in the previous sections work in vector form if the scalars p and v are replaced by vectors p and v. Each vector equation represents three scalar equations. For example, represents three equations. The kinetic energy equations are exceptions to the above replacement rule. The equations are still one-dimensional, but each scalar represents the magnitude of the vector. For example, each vector equation represents three scalar equations. Often coordinates can be chosen so that only two components are needed, as in the figure. Each component can be obtained separately and the results combined to produce a vector result. A simple construction involving the center of mass frame can be used to show that if a stationary elastic sphere is struck by a moving sphere, the two will head off at right angles after the collision. Objects of variable mass. The concept of momentum plays a fundamental role in explaining the behavior of variable mass objects such as a rocket, ejecting fuel, or a star accreting gas. In analyzing such an object, one treats the object's mass as a function that varies with time, m. The momentum of the object at time t is therefore p equals mv. One might then try to invoke Newton's second law of motion by saying that the external force F on the object is related to its momentum p by F equals dp dt. But this is incorrect, as is the related expression found by applying the product rule to d dt. This equation does not correctly describe the motion of variable mass objects. The correct equation is where u is the velocity of the ejected, accreted mass as seen in the object's rest frame. This is distinct from v, which is the velocity of the object itself as seen in an inertial frame. This equation is derived by keeping track of both the momentum of the object as well as the momentum of the ejected, accreted mass. When considered together, the object and the mass constitute a closed system in which total momentum is conserved. Relativistic mechanics. Lorentz invariance. Newtonian physics assumes that absolute time and space exist outside of any observer. This gives rise to the Galilean invariance described earlier. It also results in a prediction that the speed of light can vary from one reference frame to another. This is contrary to observation. In the special theory of relativity, Einstein keeps the postulate that the equations of motion do not depend on the reference frame, but assumes that the speed of light c is invariant. As a result, position and time in two reference frames are related by the Lorentz transformation instead of the Galilean transformation. Consider, for example, a reference frame moving relative to another at velocity v in the x direction. The Galilean transformation gives the coordinates of the moving frame as well the Lorentz transformation gives where gamma is the Lorentz factor. Newton's second law, with mass fixed, is not invariant under a Lorentz transformation. However, it can be made invariant by making the inertial mass m of an object a function of velocity. m0 is the object's invariant mass. The modified momentum obeys Newton's second law. Within the domain of classical mechanics, relativistic momentum closely approximates Newtonian momentum. At low velocity, gamma m0v is approximately equal to m0v, the Newtonian expression for momentum. Four-vector formulation in the theory of special relativity. Physical quantities are expressed in terms of four vectors that include time as a fourth coordinate along with the three space coordinates. These vectors are generally represented by capital letters, for example R for position. The expression for the four momentum depends on how the coordinates are expressed. Time may be given in its normal units or multiplied by the speed of light so that all the components of the four-vector have dimensions of length. If the latter scaling is used, an interval of proper time, tau, defined by as invariant under Lorentz transformations metric signature has been used. Different authors use different conventions. Mathematically, this invariance can be ensured in one of two ways. By treating the four vectors as Euclidean vectors and multiplying time by square root -1, or by keeping time a real quantity and embedding the vectors in a Minkowski space. In a Minkowski space, the scalar product of two four vectors u equals and v equals is defined as in all the coordinate systems. The relativistic four-velocity is defined by and the four-momentum is where m0 is the invariant mass. If R equals, then using Einstein's mass-energy equivalence, E equals mc2, this can be rewritten as thus. Conservation of four momentum is Lorentz invariant and implies conservation of both mass and energy. The magnitude of the momentum four-vector is equal to m0c, and is invariant across all reference frames. The relativistic energy-momentum relationship holds even for massless particles such as photons. By setting m0 equals 0, it follows that in a game of relativistic billiards, if a stationary particle is hit by a moving particle in an elastic collision, the paths formed by the two afterwards will form an acute angle. This is unlike the non-relativistic case where they travel at right angles. Generalized coordinates. Newton's laws can be difficult to apply to many kinds of motion because the motion is limited by constraints. Many such constraints can be incorporated by changing the normal Cartesian coordinates to a set of generalized coordinates that may be fewer in number. Refined mathematical methods have been developed for solving mechanics problems in generalized coordinates. They introduce a generalized momentum, also known as the canonical or conjugate momentum, that extends the concepts of both linear momentum and angular momentum. To distinguish it from generalized momentum, the product of mass and velocity is also referred to as mechanical, kinetic or kinematic momentum. The two main methods are described below. Lagrangian mechanics. In Lagrangian mechanics, a Lagrangian is defined as the difference between the kinetic energy T and the potential energy V. If the generalized coordinates are represented as a vector q equals and time differentiation is represented by a dot over the variable, then the equations of motion are a set of n equations. If the coordinate g is not a Cartesian coordinate, the associated generalized momentum component π does not necessarily have the dimensions of linear momentum. Even if g is a Cartesian coordinate, π will not be the same as the mechanical momentum if the potential depends on velocity. Some sources represent the kinematic momentum by the symbol π. In this mathematical framework, a generalized momentum is associated with the generalized coordinates. Its components are defined as each component pj is said to be the conjugate momentum for the coordinate qj. Now if a given coordinate g does not appear in the Lagrangian, then this is the generalization of the conservation of momentum, even if the generalized coordinates are just the ordinary spatial coordinates. The conjugate momenta are not necessarily the ordinary momentum coordinates. An example is found in the section on electromagnetism. Hamiltonian mechanics. In Hamiltonian mechanics, the Lagrangian is replaced by a Hamiltonian that is a function of generalized coordinates and momentum. The Hamiltonian is defined as where the momentum is obtained by differentiating the Lagrangian as above. The Hamiltonian equations of motion are as in Lagrangian mechanics. If a generalized coordinate does not appear in the Hamiltonian, its conjugate momentum component is conserved. Symmetry and conservation. Conservation of momentum is a mathematical consequence of the homogeneity of space. That is, conservation of momentum is a consequence of the fact that the laws of physics do not depend on position. This is a special case of Noether's theorem.